Hello! Today I'm eager to tell you what happens if you take an ordinary cycloidal reducer and then fold it into a straight line. Well, not so straight actually. Let's better go straight to this fascinating demo. As you can see here, the actuator is made out of 4 plates, 2 of which are guiding plates for alignment and 2 are pushing sliders. In this device, sliders travel in circles with a radius of 1 mm relative to the alignment plate. Sliders are 100 degrees out of phase. Travel trajectory is defined by eccentrics mounted on shafts of 2 motors that run synchronously. All 4 plates have slots. Sliders have cycloidal cutouts, alignment have linear pass cutouts. Now let's add the carriage. It has pins which are ideally an integral part of the carriage. All cutouts have a width equal to the pin's diameter and they engage with the edge of the cutouts. Cutouts in the plates define the exact position of the pin at every moment of time. Pins and the carriage, respectively, are pushed along the axis due to the motor's rotation. In total, one full rotation gives us 2p, or 6.28 mm of travel, or in other words, 10 mm of useful travel corresponds to 1.59 revolutions. In full step mode, it takes 32 steps for 1 revolution of the internal shaft, 63.68 turns of the internal shaft for the single main shaft revolution, and 1.59 main shaft revolutions to slide the carriage from start to finish, or 3240 steps in total. In the ideal world, it's approximately 3.1 micrometers of linear movement per step. Since I'm not satisfied with the current situation with parametric curves and offset tools in FreeCAD, I wrote a small Python script to generate SVGs for import. Parts I have prototyped with FDM, which took me a couple of iterations. And then I milled my parts with a 1mm end mill out of 2mm thick aluminum strip. Using FreeCAD as a CAM has its drawbacks, and at this point I think it might be reasonable to generate G-code in the same Python script, skipping the FreeCAD part at all. Linear cycloidal drive has following advantages. It has no screw drive, it has a slim planar design, and it has a great step distance in theory. Also, it has disadvantages. First of all, it's a really large backlash, and it has a high resistance, resulting in low pushing force because the pins are engaged with the edges of the cutouts. And we have some possible improvements. First of all, is to add one more phase to get a 100-degree difference between the moving slides instead of 180. We can also add miniature bearings, and also it could be possible to add motor synchronization or a feedback loop. I think that's it for now. All of the files from this project you can imagine, you can also find on my GitHub. Thank you for watching and see you later.